I want to start chapter 14 with a brainstorming exercise. Okay? Chapter 14 is getting us into the identities of acids and bases. And before I actually start going into what makes an acid and what makes a base, I just want to very quickly run down a list of what acids and what bases we know. Okay? So let's header this acids and let us both on the Zoom and in person, let's brainstorm together and name the acids that we know that we've encountered one place or another. Just start naming acids and don't use the chat, just unmute a mic and actually say something as we're naming these acids, okay? Tell me an acid. Go. I was about to hear something in the Zoom room, and I was wondering if I was going to hear the same thing. But nope, the classroom got it. Hydrochloric acid. HCl is where we start these stories. HCl is the one that we've had the most encounter with when we actually use acids in laboratory circumstances. Okay? But there are many other acids we've come across at one point or another. Sulfuric acid, awesome. The acid in lead acid car batteries. Good show. Give me another acid. And I don't just need acids that we've gone over in nomenclature in Gen Chem 1, although if you remember acids we went over in nomenclature in Gen Chem 1, that is certainly a positive. But any acid you might have encountered at any point as you've gone through your education. Citric acid. Hold on, Zoom room, I'm coming back to you in a moment. Because the classroom went citric acid. Okay? Citric acid is central to our metabolism reactions. Okay, who said what in the Zoom?
Boric acid.
Boric acid, okay. We didn't have boric acid in the 8 a.m. hour, but that is a acid with industrial purposes, and that's a good one to mention. Give me another example of an acid. Say again. Nitric acid, sure. Nitric acid is a strong industrial acid. Okay? Give me another example. Carbonic acid. We're talking about biologically relevant stuff. Carbonic acid is something that needs to get mentioned as how we regulate the pH in our blood. Okay? Sweet. Other examples.
Phosphoric acid.
Phosphoric acid, absolutely. You look in carbonated beverages, and you come across phosphoric acid more than a little bit. Okay? Have you started noticing I'm putting these into 2 columns? Okay? I'm not being just casual about that. I'm actually trying to show off something here. I want to know if you actually see a pattern in what I'm doing as I go through. Okay? Any other examples you can think of off the top of your head? Now, every single acid we've come across thus far has had the IC acid suffix to it. Okay? And the overwhelming majority of them have run around without prefixes at all. When you've studied how acids are named in the past, are there any patterns to the naming of acids that we haven't explored here? Are there any other names of acids that don't follow the IC acid suffix pattern? What's the formula of nitric acid? Yep, it's HNO3. Isn't there another acid that has nitrogen in it that has a very similar but subtly different formula? Yep. What do we call that? HNO2 is the formula I got. What do we call that? That's the pattern breaker in how these acids are named. Okay? Remember that the IC acid suffix corresponds with ions that have the ATE suffix in their name. NO3 minus is nitrate ion. It corresponds to nitric acid. Sulfuric acid, what's the formula of sulfuric acid again? There's an old rhyme that will help you remember the formula of sulfuric acid. It goes like this: Pearson was a chemist, but Pearson is no more. For what Pearson thought was H2O was H2S. Isn't it a wonderful rhyme? It's horrid. You'll never forget sulfuric acid's formula again. Okay? And I could go down the list. Phosphoric acid is H3PO4. Carbonic acid is H2CO3. Boric acid is H3BO3. Citric acid is H6C5O7. I think it doesn't follow anywhere near that pattern. I'm not going to write up the formula of citric acid. Citric acid is a big honking acid. Okay? But it's not size that's dictating how I'm classifying these. How about hydro acids? How about acids that start with hydro as the prefix? What other acids act like that beyond hydrochloric acid? Take a guess if you're not 100% sure. If you recognize a pattern, you may have it right. In the hydrocyanic acid. That is actually a thing. It doesn't quite follow the pattern of the other hydro acids. It's HCN. I was actually going somewhere else completely with a hydro prefix. to another place. Hydrochloric. What's below chlorine on the periodic table? You may look up a periodic table if you've got it to see. Yeah, HBr, hydrobromic acid. Now I'm starting the left column again. And what's below bromine on the periodic table? Iodine, sure. So HI then would have what name? HCl is hydrochloric acid and HBr is hydrobromic acid. HI would be hydroiodic acid, absolutely. Okay? Oh, who have I left out among those halogens in the next to last column of the periodic table? What element? I've got chlorine, I got bromine, I got iodine. Fluorine. What's that guy named? HF. Hydrofluoric acid. Oh, I just broke my pattern again. If you started to know where I was going with hydrochloric, hydrobromic, hydroiodic, I just completely broke the pattern of hydrofluoric. Okay, we've got a great list there on the right-hand side. Let me fill in one more on the left-hand side, which doesn't typically get talked about in Gen Chem, but really winds up being important later on in your chemical education. It's one of the most substantial acids we can come across. It's called perchloric acid. It's derived from the perchlorate ion, which is the maximum number of oxygens I can have with chlorine. It's HClO4. Okay. Has anybody picked up on the pattern between the left-hand column and the right-hand column yet? I just about gave away the store while I was talking through. Yeah, they're strong and weak acids. That's exactly what I'm on about here. Everybody on the left is a strong acid. Everybody on the right is a weak acid. What's the difference between a strong acid and a weak acid? What is it that makes a strong acid strong? Like I said before, it's not size. And it's not anything that has to do with its capacity for reactivity. Okay? Phosphoric acid is very, very reactive. Hydrofluoric acid is very, very reactive. But they have differing behaviors when dissolved in water. Let me take hydrochloric and hydrofluoric acids, and let me make those my two core examples for this distinction between strong acid and weak acid behavior. Catch your scratch. Okay. Remember that hydrochloric acid is nothing more, nothing less than the hydrogen chloride molecule dissolved in water and combined with liquid water chemicals. And hydrofluoric acid is nothing more and nothing less than the hydrogen fluoride molecule dissolved with water and combined with water chemically. And when we actually see that reaction happen between hydrochloric acid and water, that reaction immediately goes to products and generates hydronium ion and chloride ion. Okay? Now, I've spent a good couple weeks in this course talking about equilibrium. I've spent a good couple of weeks talking about reactions that go both to the left and to the right. Notice what I did not draw on the reaction with HCl and water. That's not an equilibrium arrow. That's going straight to the right. And that's going straight to the right and being done. When you dissolve hydrochloric acid in water, you get the hydrogen ion on chlorine transferring to the water to make this hydronium ion. And breaking off the chloride as well. Now, many of you who've studied this previously may have seen this reaction written as HCl yields H plus Cl minus. And just saying HCl by itself breaks up into hydrogen ions and chloride ions. Okay? For the benefit of those of you whose chemical education goes on from here, who have organic chemistry in your future, I want to write this reaction very intentionally with water participating in the reaction, because it's easier to understand where the hydrogen goes when there's a water running around to pick up the hydrogen and carry the hydrogen with it. We're going to find, as we do chemistry going forward with acids and with bases, as we're going to mention here in a little while, that the presence of the hydronium ion is going to be our signature for the presence of acid behavior. Okay? Regardless, the fact that that arrow in the chemistry goes straight to the right reflects the reality that strong acids dissociate completely. Strong acids break up. And I have, for every practical purpose, no hydrogen chloride molecules dissolved in water left when hydrochloric acid is generated. And I have hydronium ions running around and chloride ions running around. There's nothing left on the left-hand side. Everything's gone to products. Okay? Well, that's nice, Pearson. Why did you spend so much time going over equilibrium if this is just going to go to products? I did it for weak acids. And I'm going to write my equilibrium arrow here for this reaction a little bit differently than you've seen it before, and possibly a little bit more descriptively than you've seen it before. Little bit to the left, a lot more to the right. I forgot my aqueous on the chloride ion up here. It turns out that uniquely among all of the acids that are based off of halogens, hydrofluoric acid, the hydrogen fluoride molecule dissolved in water, doesn't want to break apart as readily as the hydrogen chloride molecule. In fact, it really doesn't prefer to break apart at all. If I get put in a situation where I've got hydronium ions running around, signature of acid running around with fluoride ions, I prefer to make hydrogen fluoride molecules. But when I do dissolve hydrogen fluoride molecules in water, I get a little bit of hydronium ion and a little bit of fluoride ion being generated. I get a lot of hydrogen fluoride molecules staying intact. Weak acids do not dissociate completely. Weak acids don't have electrolytic behavior like strong acids do. Now, you don't want to swallow sodium. You don't want to swallow hydrochloric acid and call that a strong electrolyte and call that contributing to electrolytes in your body. There are other problems with using hydrochloric acid as a strong electrolyte. But because it's generating ions in such substantial quantities, we do consider a strong acid solution a strong electrolyte. Something that generates a lot of positive and negative ions in solution. Okay? And we consider weak acids to be weak electrolytes. Now, what do all these acids have in common? Well, I come back up here and look at all of these formulas. that we wound up writing down one way or another, what do all of those formulas have in common with one another? The obvious thing, H in front. That's what they all have in common. And when they go through their reactivity, regardless of whether they're strong or weak, that H in front is getting given up to the hydronium ion, and the negatively charged ion is being left behind. We say that all acids are hydrogen ion donors. In their behavior in solution, all acids give up hydrogen ions to the solution. And in our application, we're dealing in aqueous solution pretty much all the time here. We say that all acids are giving up hydrogen ions to water that's present. Okay? Are we good with acids? Got a half decent sense of what we're working with acids? Counterpart to acids are? Oh, come on, don't leave me hanging like this. If I've talked about acid chemistry, now I have to talk about base chemistry. Absolutely. I won't make you brainstorm with bases the way I made you brainstorm with acids. Bases tend to be a bit more obscure. I do think there's one base that most of you recognize. Typically, when we take HCl in a reaction setting and we neutralize it, that neutralization of HCl is with what compound? We neutralize hydrochloric acid with what? Sodium hydroxide is the canonical strong base. Both in the general chemistry lab and in practical industrial labs and every place in between, if you need a strong base, very frequently you go with sodium hydroxide. Sodium hydroxide is very, very accessible and relatively cheap. Okay. There's a list of 6 strong acids that we worked out before. The list of strong bases is going to be 6 deep as well. It's going to be 3 of these bases that have alkali metals associated with them. So sodium hydroxide and lithium hydroxide and potassium hydroxide. And then we'll have 3 bases that are associated with the alkaline earths. And down the periodic table there, calcium is the one that will come across its highest up. And then we go down further to places we don't normally go on the periodic table. We go to strontium hydroxide. And we go to barium hydroxide. And in both cases, on both of these lists of strong acids and strong bases, we pretty much have them listed in the order of importance of memorization. Okay? It's really nice to have all 6 strong acids known and all 6 strong bases known. And beyond that, anything that we might come across in Gen Chem that's not one of those 6 strong acids and 6 strong bases, we're going to characterize as a weak base or weak acid. Now, what does it look like the bases have in common? I can even write down their formula if you'd like for me to. Sodium hydroxide is NaOH. Lithium hydroxide is LiOH. Potassium hydroxide is KOH. Calcium hydroxide is CaOH2. Strontium hydroxide, SrOH2. Barium hydroxide, BaOH2. Seems to be a theme here. I can just doodle down some strong base reactivity. I don't even need water around for this. I can just doodle down NaOH, an aqueous solution. And again, because it's strong, this is a right-hand arrow going completely to products, generating sodium ions and hydroxide ions. And what's more, when I actually go to start building my list over here of the weak bases, I can build off the same pattern. Magnesium hydroxide is a weak base. Aluminum hydroxide is a weak base. Aluminum hydroxide, the Al ion has a 3+ charge, so that's AlOH3. And let's see, what else could I mention? I could totally mention beryllium hydroxide, BeOH2. Okay. I could go on with every metal compound. Iron hydroxide, FeOH3 for iron 3 hydroxide. Okay. Silver hydroxide, AgOH. I could go down the list. And the hydroxide theme is really holding well. But apart from sodium hydroxide, the most common base that you run into in your kitchen as a cleaning agent completely breaks this pattern. Anybody know what base I have not mentioned that breaks this pattern? Ammonia, aqueous ammonia, NH3, and that's it. Well, let's look at ammonia's reactivity. Ammonia's reactivity doesn't make sense when we just consider NH3 on its own. We need to consider NH3 in reaction with the water it's dissolving in. NH3 plus H2O is a liquid. And again, this is a weak base. It doesn't completely favor products. It favors reactants a little bit more, hence the way I draw the equilibrium arrow, with a little bit of favorability towards the left side rather than the right. But when aqueous ammonia is dissolved in water, it actually picks up a hydrogen ion itself. And the NH3 picking up a hydrogen ion makes it the NH4 plus ion, the ammonium ion. And OH minus comes out on the other side. Now that's a little bit satisfying. After all, the OH is showing up. That's going to be our signature for basic solution being present, is the presence of that OH minus ion. But where's the OH minus ion coming from? Not the NH3. Has to be coming from the water. There are actually two competing definitions of what makes a base. One based on what you commonly know, and a second that's based on what chemically is happening when bases are dissolved. The definition based on what you commonly know is owed to Svante Arrhenius. The Arrhenius definition of a base is a hydrogen ion donor. And obviously the Arrhenius definition of a base explains all this fleet of hydroxides and the rationale behind all of these hydroxides having basic behavior to them. But it doesn't explain anything about why ammonia is a base. And when you run into organic bases, those of you who have organic chemistry in your future, the Arrhenius definition is very poor at explaining basic behavior for those type of compounds. We need a different definition. And the different definition that we wind up using is the definition of two men named Bronsted and Lowry. And Bronsted is Scandinavian, so what I really need to do if I'm going to actually complete the Bronsted-Lowry definition of a base is I need to put a little slash here through the O on Bronsted. That's actually far better than anything I did in the 8 o'clock hour. Bronsted and Lowry. And the Bronsted-Lowry definition of a base is not centered around what's donated, but centered around hydrogen ions. The Bronsted-Lowry definition of a base is a stuff that's a hydrogen ion acceptor. We can explain the hydroxide ion as a base because it very readily takes up hydrogen ions itself to make water. That's the acid equilibrium story we mentioned at the very end of class on Tuesday, and that we'll mention again next Tuesday. But we need the Bronsted-Lowry definition of a base to help explain why ammonia has basic behavior. And we need the Bronsted-Lowry definition of a base to explain other types of basic behavior as well. Let me tell one type of dissociation behavior for a weak acid. And for a weak acid that's polyprotic, that has a whole lot of hydrogen ions beyond just one to contribute. So let me tell a carbonic acid story. What's the formula of carbonic acid again? H2CO3. Yes, indeed. Now, I need y'all to do me a favor here. Even if you're not the best of note takers, I need you to write down this particular reaction for me. Carbonic acid, aqueous, dissolved in water. Let me actually make this plain. Put some care into this. Plus 2 H2Os as a liquid. And that will be responsible for the dissociation of carbonic acid into 2 H3O pluses. And CO3 minus. What do we call the CO3 2 minus ion? It's a carbonate ion. Okay? Everybody got this down? Then do me one more favor. Draw an X through that and make sure you never write anything like that again. The reason I want an X through this is because it represents all of the breakup of hydrogen ions off of carbonic acid happening at once. And I don't want to represent that type of dissociation happening immediately all at once. I want to represent that dissociation happening stepwise. And that dissociation is important to represent one step at a time. The most accurate first dissociation of the carbonic acid molecule dissolved in water plus one H2O here. Remember how I mentioned on Tuesday that a lot of the reactions we're going to work with, especially in acid-base chemistry, have one-to-one stoichiometry? We're going to lean on one-to-one stoichiometry very, very hard. And not just because it's more convenient, because it actually represents what's happening. I'm only going to break one hydrogen ion free from the carbonic acid molecule. If I only break one hydrogen ion free from H2CO3, what gets left behind? H2CO3 is carbonic acid. HCO3 minus is the hydrogen carbonate ion, or more commonly, the bicarbonate ion. Leave a little extra space, note takers, underneath carbonic acid and bicarbonate, so we can add one more line of information to this. But let me complete the dissociation here. Colors. Now I'm going to make that right-hand arrow very, very small this time, because the second dissociation is much more reticent than the first. It's much less likely to happen. But when it does happen, it does give me H3O plus and CO3 2 minus. Okay. Now, on the reactant side of the very first reaction here, what's our acid? Simple, stupid, obvious. On the left side of this reaction between H2CO3 and H2O, the acid is, it really is carbonic acid. I'm not trying to trick you. Okay. And it is, after all, carbonic acid that is, by our Bronsted-Lowry definition of an acid, giving up a hydrogen ion. Where's the hydrogen ion going? Because the Bronsted-Lowry definition of a base is a stuff that accepts a hydrogen ion. Carbonic acid is giving up the hydrogen ion. Who's accepting it? What else is involved in the reaction? Good old water. Water is accepting a hydrogen ion and being transformed into hydronium ion. Yes? So water is a base. That's not how we've been taught to think about water. Okay? Water is neutral. Water is not acid, nor is it base. That's what we've been taught, right? But Bronsted-Lowry come alongside and say, no, anything that gives up a hydrogen ion is an acid. And anything that accepts a hydrogen ion is a base. Well, I can go down to the second reaction and tell the same story then, can't I? Because the bicarbonate ion is giving up a hydrogen ion and leaving carbonate behind. And water, once again, is taking on that hydrogen ion. Water, in both cases, is taking on that hydrogen ion. And H3O plus is what's left over. Bicarbonate ion behaves as an acid. Water, again, behaves as a base. Is everybody comfortable with the idea of dealing with water as a base? Okay? Don't get too comfortable with it. It's weird. We've been taught that water is neutral. It's okay to still have that idea that you've been taught and say, well, if Pearson's going to come around and tell me something different, then why was I ever taught that water's neutral in the first place? Let me tell one more story. Let me actually bring back a different story. Let me bring back the ammonia story again. And we've already talked about this reaction here. Aqueous ammonia with water generates the ammonium ion, NH4+. Plus what? What's left over? Hydroxide. Okay? Well, who's donating a hydrogen ion now? Water. Water's taking an extra hydrogen and kicking the hydrogen over to ammonia. That arrow's going the other way. So water this time is the hydrogen ion donor. Water this time is the acid. And ammonia, as we've been told, is the thing that's accepting the hydrogen ion. Ammonia is acting as the base. So Bronsted-Lowry, in their definition of acids and bases, particularly bases, the Bronsted-Lowry definitions are not here to take your idea of water as neutral and completely undo it. What Bronsted and Lowry are here to do is to say what dictates what is an acid and what is a base is context dependent. Anything that gives up hydrogen ions is an acid. And anything that accepts hydrogen ions is a base. And that means some things can behave as an acid or as a base, depending upon context. And absolutely at the center of that list of things that can behave as an acid or as a base is water. But water is not the only thing that can behave as either an acid or as a base. Go back to the carbonic acid story up here. Carbonic acid reacts with water to produce the hydronium ion and bicarbonate. Now note how that equilibrium is drawn. It's drawn in a way that really favors the left-hand side. It's drawn in a way that favors reactants. So bicarbonate can just as readily react with hydronium ion that's present to generate carbonic acid and water. If we look at this reaction here in the reverse fashion, with the right side shifting left, well, who on the right side is acting as the acid? Who gives up hydrogen ions among what's on the right-hand side? Going back left. The hydronium acid, the hydronium ion acts like an acid when reacting with the bicarbonate ion. And bicarbonate would then react as a base. Even though bicarbonate, when reacting with water, behaves as an acid. Now, it's really helpful when I go through stories of this sort to talk about the sidedness of this reaction and talk about a partnership between the carbonic acid molecule and the bicarbonate ion, between the water molecule and the hydronium ion. Okay? And we're going to coin a term, conjugate, to represent the relationship between carbonic acid and bicarbonate. If carbonic acid behaves as an acid, then the thing that has hydrogen ions given up, bicarbonate, is carbonic acid's conjugate base. And if water is behaving as a base, taking on hydrogen ions, then the hydronium ion behaves as water's conjugate acid. And that's true in both cases. Regardless of circumstance, regardless of behavior, every base has a conjugate acid. Every acid has a conjugate base. The conjugate acid, bicarbonate here is behaving as an acid. The conjugate base of bicarbonate is what? The carbonate ion. Go back to the ammonia example. In the ammonia example, water acts as the acid. Water's giving up the hydrogen ion. What is water's conjugate base? What's resulting once water's given up its hydrogen ion? Hydroxide. Water is the acid. The hydroxide ion is its conjugate base. And ammonia is the base. Ammonia is the thing receiving the hydrogen ion. Ammonia is the base. What's the conjugate acid? Well, what's left? Ammonium. And it's plain to see how ammonium can be acting as an acid because of the capacity of the ammonium to give up H+. It's plain to see how OH can be acting like a base because OH- has the capacity to take on an H+. Okay? One other very common example in these contexts is the phosphoric acid example. What is the conjugate base of H3PO4? What would be the species that would be left behind if H3PO4 went and gave up a hydrogen ion? It would be H2PO4 1-. We call H2PO4 the dihydrogen phosphate ion. But the reality of dihydrogen phosphate's existence is it can very readily give up it's still got two hydrogens to give up, right? It can give up a hydrogen on its own. So dihydrogen phosphate is not just a base. It doesn't just have the capacity to take on a hydrogen, go back to H3PO4. H2PO4 minus has the capacity to be an acid itself. And if H2PO4 minus is an acid, what is its conjugate base? What results when H2PO4 minus gives up a hydrogen ion? Follow the pattern. Monohydrogen phosphate, if you will. But nothing in the rules says that monohydrogen phosphate can't act as an acid. It still has the one hydrogen to give up after all, yes? So let's just go through the story one more time. HPO4 2 minus is an acid. What is its conjugate base? What results when HPO4 2 minus gives up its last hydrogen? Well, that's just the phosphate ion left behind. That's just PO4 3 minus. Okay. Carbonic acid and phosphoric acid are examples of polyprotic acids. They're examples of acids that have the capacity to give up more than one hydrogen ion. They stand in contrast to the monoprotic acids like hydrochloric acid and nitric acid. But even the polyprotic acids, we will always consider them giving up one hydrogen ion at a time. We'll never talk about them tossing off three hydrogen ions at once. We'll never talk about carbonic acid tossing off two hydrogen ions at once. We'll always talk about the polyprotic acids giving up their hydrogen ions one hydrogen at a time. Now, we work with the textbook a lot. Sometimes I don't get agitated about you reading the textbook because it does okay, but it's not great, it's not awful. Sometimes I actually will warn you away from a couple sections of the textbook because they go into deep detail. But sometimes I say what's in the textbook is gold, and especially if your chemical education goes on beyond Gen Chem 2, you will carry what's in the textbook with you. Section 14.1 of the textbook, you will carry with you. The descriptions of acids and conjugate bases in section 14.1 goes beyond the examples I've given out here today. It's really, really good stuff. Carry it with you. Okay? I owe you some time back. Let's say one more thing, then I'll be done for the day. Okay? I'm on the brink of having assessment 2 ready. I could have assessment 2 ready to launch this time next week. I'm not 100% certain I want to, because what's next in chapter 14, I want to make sure we've gone over completely, and I want to make sure we're comfortable with. What's next in chapter 14 is taking the equilibrium stuff that we've been talking about and bringing the acid-base stuff that we're into now in contact with it, and talking about acid equilibrium, and talking about standard means to take an acid solution and determine the hydrogen ion concentration, the hydronium ion concentration of that solution. And by so doing, determine the pH of that solution. I want to make sure we get that right. And when I release assessment 2 is entirely going to depend on when I feel like we've covered it enough in lecture and we've got that right. Okay? It's coming. It's coming in the not too distant future, but when it's coming is very dependent on how lecture goes from here. I will tell you that assessment 2 will cover chapter 12 in full, chapter 13 in full, and the first half of chapter 14. I'll tell you exactly what section that cuts off on when I'm there. But it's roughly the first half of chapter 14. Okay? We all good? Yeah, I've taken you well beyond 10:45 many days. I don't need to take you well beyond 10:45 today. Let's be done.